Okay, we're going to spend some time talking about binary numbers today. If you're looking on our website under week 2, this I'm going to be referring to the handout, More Notes on Binary Numbers. So when you select that link, it should open up a document like this. Read through these things, watch the video links. It's really good information here. Basics is when we're talking about a binary number system, it's a base 2. We are very familiar with our base 10 decimal system where we have values 0 through 9. But in a binary system, they have 2 digits, so it's a 0 and a 1. These can be handy when programming because we can represent that as maybe a true or false or a high or low voltage. So base 2 is pretty effective when dealing with computer programming. So let's start talking about binary system is a positional number system. It has a place value, and each place value is increasing. Each place value that you move to the left is increasing twice as much as the place value to the right. Whereas we in base 10 systems, as we move to the left from a 1 to a 10, from a 10 to 100, each jump there is a times 10. In a base 2, each jump to the left is a multiplication of 2. And so let's start practicing a little bit about this. So here's an algorithm that will help us convert a number from binary to decimal. So we have a binary number, let's say converting from binary to decimal. So the binary number is 10101. What we'd want to do then is to get our place values for our base 2 system. Remember, each place value jumps by 2, so we have the ones place, and then the next one is going to be times 2. Following over, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and so forth. So then the next one would be 32, then 64, etc. So you start with the ones place here, and you put your binary number underneath that number line. And everywhere that there is a value for a 1 in your binary, you take the place value from above and you add them up. So we have our place values for our binary system, and we have our binary number here. So we're going to convert it into decimal. So this is turned on, the ones place is turned on, the 4 is turned on, and the 16 is turned on. So we would add those up. 16 plus 4 plus 1 equals 21. So 21 represented in binary is 10101. Okay. Moving down here, converting decimal now to binary. So say, for instance, we have a decimal number 25, and we want to convert that to binary. We need to have our binary place value number line. So 1, 2, 4, 8, 16, 32, and so forth. So what we want to do is we want to take the number, the decimal number that we are trying to convert into binary, and we take it underneath our binary number line, and we try to find the value that can be taken away from our number, the largest value that can be taken away from our number. So we take the largest chunk we can. As we move through this line, I can't take 32 from 25, but I can take 16 from 25. So I turn on my 16, and that leaves us, when I take 16 minus 25, I have 9 left. Well, I can continue the algorithm here. I can take 8 from 9, so I turn on that place value, leaving us with a 1, remainder of 1. I can't take 4 from 1, I can't take 2 from 1, I can't take 1 for 1. Then you're going to fill in the remainders, the place values that don't have assignments, with 1s, with 0s. So then we have converted 25 into binary as 11001. So when we're starting to deal with very, very large numbers, like a million in binary is this number here, that is still quite a few digits to be dealing with. So what we want to do is create other means for representing large numbers, such as a million or high numbers like that. So what we have a system called octal numbers, and we also have a system called hexadecimal numbers. Octal numbers has a base 10 number system. So each value jumping over from to the left is a multiple of 8. So we have a ones place times 8 is a 8th place, then times 8 is a 64th place, times 8 is a 512th place, and so forth. We can represent all values of the octal base 8 system in the numbers 0 through 7. Remember, in our base 10 system, our values are 0 through 9. In our base 2 systems, it's 0 through 1. So in an octal system, we have values 0 through 7 that can be broken down and represented in binary. So what we have here is the binary 0, 0, 0 is converted to the octal system of 1. And we just make, this is our binary number line. If we wanted to look at this a little bit closer as our binary values, 0, 0, 0 is that. So if we have, I'm going to give you a number line here that you're going to like to look at a little bit. So if we have a number that we want to convert from binary to octal, we need to group these. We need to take a look at this a little bit closer here. So we have on our binary, so 0, 0, 0 is still 0. Now, if I'm converting this, 1 in binary is 0, 0, 1. 2 in binary is 0, 1, 0. 3 in binary is 0, 1, 1. Let's take a look at, like, say, number 5. 5 in binary, 101. So we come to our number line over here. If we wanted to see if that was right, 101, this would be 4 plus 1. That would be 5. So we can see that how we work this is first you need to convert anything you want into a binary system, and then you break them into chunks of 3 and assign an octal value for those. And it reduces the amount of information to represent a decimal number. So for instance, here is the number 1 million. If I were to break those into chunks of 3, it would look like this. This is that same value there. So I take my binary number, break them into chunks of 3, and then assign an octal value for them. So 0, 0, 0 is 0. Same thing here, 0, 0, 1. We find that the octal value is 1. Same here, 1, 0, 0. I look down here, 1, 0, 0, that's 4. 1, 1, 0 is 6, and 0, 1, 1 is 3. So an octal 1 million is represented as 3,641,100. There is also hexadecimal numbers. So another more economical way is to represent numbers in a hexadecimal or a base 16 system. So in a base 16 system, we have place values of 0 through 15. We're going to represent 0 through 9 with numbers and 10 through 15 with letters A through F. So as again, just the same, we have a ones place, has a value of 16 to the 1. We have a 16th place, 16 to the first power. We have a 256th place, which is 16 to the second power, and so on. The same thing that would go to create a number from decimal to octal, you do the same thing, only instead of breaking it into chunks of 3 here, we are going to be breaking them into chunks of 4, and then assigning a hexadecimal value for those. Again, these are binary terms, so if we were to look at number 9 here, let's just say 9 is 1001. We can confirm that 9 is going to be 1001. 1001. If we look at this here, making sure that everything lines up, that's going to be 8 plus, 001, and that would be 1. So that would be 9. So 1001 is in fact 9. So that's how we can convert that. So what we would do simply is to take your decimal number, break them into chunks of 4, and then assign a hexadecimal value for that. So when we get to like 1111, that is 15 in binary. If we look at that, again, 4 ones in a row in decimal. Eight plus 4 is 12, 13, 14, 15. So that we can see is how that works. Okay, so in 1 million, the hexadecimal value is F4240. All right, I'm going to work through a problem real quick using this handout that I'm going to attach to you. I'm going to take a number a decimal number, let's just say our decimal number is going to be, let's just go 575,243. Let's just say that. Now, so we're going to have a little bit over 500,000, 575,000. So first thing, I'm going to convert this to binary. Then I want to convert it to octal. And I want to do it to hexadecimal. Hopefully this will work out pretty quick. All right, so we need to find the largest value I can take. So I have 575,243. If I go through my number line trying to take the largest value I can, I'm coming way over here. Okay, 524, I can take that. So I'm going to, on a calculator, let's just do this so I don't make any mistakes. So I have my value that I'm working with in decimal, minus out the largest value I can, which is going to be 524,288. So I have a remainder now. I'm going to put a 1 there because I did activate that place value. So I have a remainder of a little over 50,000. So I'm going to take the largest I can from that, which is 65 is too large. So I can take that 32, the 15th placeholder here. So I'm going to take that number. I'm going to minus out this one here, 3, 2, 7, 6, 8. So I have 18,000 left over. I want to make sure that I do mark that place value as being turned on. We're using it. So now I have 18,187 coming through here. I can take 16 from that. So I'm going to take that value from here. So I'm going to minus 16,384. And I have 1,803 left. So I did take and make sure I activate that place value. 1,803. I can go right here, 1,204. Oh. Oop. Hold on. Okay, so I'm taking 1,803 minus 1,024. I have 779 left. I can take that 512 here. Minus 512. I have 267 left. I can take that 256 out of that. I have 11 left. I can take 8 from that. I have 3 remainders. So I'm going to activate my 2. I have 1 left. So then I put that in there, 1. All right, the rest are zeros. Okay, so this here now is my binary number for my decimal value of 575,243. So let's put that one right here. I'm going to do, okay, so I can get this right. 1 0 0 0 1 1 0 0 0 1 1 1 0 0 0 0 1 0 1 1. Okay, there. Let's make that large. Okay, so here's our binary number for our 500,000 number. Now what we're going to do to create an octal value for that is that we need to then break them into threes. I'm going to move to this next page, or octal. Here's our number that we're working with. And I'm going to need to break those into chunks of 3. And I'll do that here. Okay, so I took our binary number and I broke it into chunks of 3. So we then need to assign those values to an octal number here. So 0, 0, 0 has an octal value of 0. Again, same thing here. 100 is represented by a 4. 0, 11 is a 3. We've got 0, 0, 1, that's a 1. And 0, 10 is a 2. So our number in binary is this. Our number in octal is 2, 1. Oh, I missed one here, sorry. So 0, 11 is a 3. I might have messed that up. 100, yeah, I did that mess up. That's a 4. 0, 0, 1 is a 1 and a 2. I believe that's correct. So our value in octal is 2, 1, 4, 3, 4, 0, 0. Okay, so there's our octal number. I'm going to just bring it back here so we kind of keep those all on the same page. Now, hexadecimal. Again, we take our binary number, we're going to break it into chunks of 4. So I'm going to move over to my hexadecimal tab here. I'm taking our number that I just brought over there like this. And I'm going to break this into segments of 4. I took our binary number, I put them into chunks of 4. So we can now convert those into hexadecimal. So 0, 0, 0 is in hexadecimal 0. So both of these are going to be 0. 0, 1, 1, 1 is a 7. 1100 is a C. And 1000 is going to be an 8. So the conversion is going to be 8C700 in hexadecimal. Okay, so that's a real quick run through. I will provide you with this handout to help you convert your binary to octal and hexadecimal and so forth. Go back and reference our handout. We talked about abstraction. Here are some practice problems that you should be able to look at. And in your portfolio, underneath reflections, I would like you to answer these. They are point assigned, so it's important that you do that. And this challenging one here, it says here, suppose we're dealing with a base 5 number system. Here's an example of how to convert 1,432 from a base 5 system to a decimal system. So the 2s, we have a 1s in a base 5. Remember, that's going to be the place values. Each one jumps up by 5. So we'll have a 0 and we'll have a 1 side. We'll have a 5, 25, 125. The next one might be times 25, which would be 625 times 25, etc. So taking your base 5 number 142, converting it to decimal, it's going to be a 242. So that might help you with this challenging question number 4. All right, if you have any questions about conversions or binary or octal or hexadecimal, shoot me an email and we can work on that together. Thank you.